So in the previous video we did boson enhancement for 2 bosons, but suppose we start with n bosons in state B and 1 boson in state A. And of course we're still trying to couple the bosons from state A over into state B. So our Hamiltonian is going to look just like a straightforward generalization of the one we had for the 2 boson case. Now once again, we've got the Hermitian term, so if we're going to couple A into B, we also have to couple B into A. And also, once again, anything we do for one boson, we have to do for all of them, because they're identical particles. And so we have to have at least that Hamiltonian. That's the simplest we can have. What's our initial state going to look like? Well, in this case, we're going to have one particle in A and all the rest in B, but we can't have a particular particle being in A, because then the coefficients are not the same when we swap any two particles. In order to have that be the case, we have to have a superposition, a positive superposition of every combination of A's and B's, so having our A in each different position. Now what do we get when we apply our Hamiltonian to this initial state? First of all, let's look at that Hamiltonian acting on this state here. So first of all, we've got an A there and all the rest are B's. So the A is in the first slot, so the only term where this is going to affect anything is the J equals 1 case. And then we're going to get that A turning into a B. So the first thing we'll get is all B terms. Then we're going to have to deal with the fact that these B's here are going to start to turn some of these B's into A's. So we're going to have a sum of n terms where each of these B's in turn is replaced by an A. And so in each case we'll have 2 A's and n minus 1 B's. And then we're going to look at this term, and again we're going to have the case where that A is turned into a B. We'll have one of those, and then we'll have n terms where one of the other B's is turned into an A. And then so on and so forth, and we're going to end up with n plus 1 of these terms where we have all B's, and we're going to have every other combination of terms where we have terms with 2 bosons in state A and all the rest in B. And indeed, there's doubling up of these terms, so there'll be multiple copies of them as well. Now remember, our transition rate is just proportional to the mod squared of the overlap between the Hamiltonian acting on the initial state and the final state. And our final state here in this case is where we've got all the particles turned over into B. And so we have n plus 1 of those divided by square root n plus 1, and then we're going to get a root n plus 1, and then we're squaring that, which is n plus 1 times mod u squared. So the more particles get transferred over into state B, the faster this process goes. That's a very surprising result. We often call this part here the stimulated process, and this part here the spontaneous process. You can see the spontaneous process is the rate that you would get if you didn't have any bosons in state B. So it's what happens if you just have a particle, a single particle, say in state A, and you're trying to couple it over into state B. That's the spontaneous process, and the stimulated process is the more particles you have in state B, the faster and faster it goes. This process whereby bosons like to be together, where they get an enhanced rate of going into states where there's already lots of bosons, is called boson enhancement, and it's basically the secret of the laser. In a laser you have a pumping process that's trying to put photons into modes of a cavity. And there are lots of different modes of a cavity, but whichever one has the most photons in it has an enhanced rate of taking energy out of the coupling. And so what happens is you have all the power from your pumping mechanism ideally going into a single mode. And so you have a large number of bosons in that single mode, so it comes out completely coherent, and that gives you all the special properties of a laser. If you're struggling for analogy, the obvious one is capitalism. If you have money, then you get given more money. And so eventually the person with the most money tends to suck all the money out of the available pool, and you have a very singular wealth distribution. The same thing happens in a laser. You have this mechanism by which the rich get richer, and pretty soon one mode has all the money, or in this case all the bosons, and so you have a complete macroscopic occupation of a single quantum state.